million complications that everybody here appreciates, you can never get it. So all you can get is an approximation of the truncated part, but that applies in a certain bandwidth. And the same thing happens to the Monday and the Friday. So when you take the difference between the two, instead of getting the difference of the real thing, you're getting the difference between what you were able to identify. The truncated difference you don't have. If it almost cancels, you're in business. If it doesn't almost cancel, there's going to be difficulty. So issues. Dan is going to comment, I think, on the state of the situation, but we, at the present time, have, I can summarize this by saying that the part that we are looking at is such that for the number of sensors that are available due to constraints, it is a tough proposition to be able to say that these loads exist, or at least exist with sufficient accuracy. We are trying to be able to answer that question. It's a work in progress, as I said, but for that we needed to do something analytical with a model of the part. So far we had problems with security, getting a handle on a model of the part. It seems like we are about to get around that. And so once we get a model of the part, then at least we'll be able to say on the ideal conditions, is this technique capable? That still will not prove that we would be able to do it subsequently, but it would at least allow us to say, within the real number model, can we hope to obtain useful information on the location?
We do the commercial part of this. Is about an aerospace structure, but mainly what we do is designing health monitoring systems. Given you have models, whether it be of a building, bridge, or aerostructure, how do you choose which sensors, where to place them, the actuators to get health monitoring coverage, which is leading to what I think is a necessary, maybe not sufficient condition to commercialization, but at least to reality. This again, the part we designed, this is a wing fitting, it holds the wing on the fuselage, and we have an algorithm that says, given all the sensors, place them thusly. And some of the complications when going to reality are temperatures. You have some crack profile that's put in, but there's also temperatures and environmental conditions that go on, that go beyond the theory, that corrupt your noise. So how do you handle those kind of things? So you see they start at 0.02 inch crack and go all the way up to 1.5 inch. And if you're monitoring your damage metric, whatever it may be, it's going to be also corrupted by the temperatures. You can see most of them, well, actually almost all of those are due to temperatures and not due to damage. Once you compensate it, you can greatly tell the difference, and it actually makes it statistically differentiable that this was the performance for uncompensated. You see you get a lot of false alarms. You really don't even detect the damage till an inch. But if you can those were the statistics, if you can compensate it, you get a lot better performance. You detect on a 0.02 inch crack, reduce the false alarms. So the problem I see for going to reality for a lot of researchers is scalability. You know, that's the main issue. That some things work in a discrete domain. It works on a 10-degree of freedom model that's very simple to handle. But how do these things scale up to large systems to make something, you know, useful in reality? Because why don't we use eddy current whenever we're doing inspections? Because you don't want eddy current every little place on there. Same thing with your processes. If you have to do you have to think about how this is going to scale up on something the size of a space shuttle, on the size of a building. You know, I think that's most of the papers I see. You're doing an example on 10-degree freedom models or some simplified structure, and that concept of how it scales up into the real world. And a lot of it's, you know, you don't have experience in doing that. You don't know these issues. You learn a lot of these hard ones. And so that's what I see as one of the issues going on to the reality.
What kind of size and dimension can you simulate with the finite element aspects?
Right. Well,
There's a microphone here.
in the, it's okay, I can speak louder. There are two parts to this. First, we have just pure data, so there is no simulation at that point, right? So this part is excited, or it could be anything else, because we've applied it to bridges and buildings and so on. But basically, we have a collection of time histories from a discrete number of sensors. So let's say, for example, 7 in this case. but it could be 10, 15, 20. I've never done anything with more than, let's say, 20 sensors. So let's say, for example, 20 columns by 15,000 rows. This is just the time histories. Now, the first stage of the process is to obtain what we would refer to as a model. So finding information that condenses this. The problem is that, as I guess you are suggesting, the real structure may have 1,000 modes, 1,000 ways of vibrate, modes, frequencies, etc. We obviously cannot find 1,000 modes. We can probably find 5, 6, maybe 10 with good accuracy. Therefore, what we are able to extract from the data is not the real reality of the structure, but just a small thing that we can see. And then we are trying to work with that.
Follow up, 4 meters, that kind of structure is, have you tried just to do that 4 meters?
No, we have done, I mean, yes, we have done on the 4 meters, but we have also done it on, let's say, 6-story buildings, not in a different application, civil engineering application. So the actual physical size, I don't think it's much of an issue, the actual physical size.
Jeff?
Is there a relationship between the data sampling density physically and the frequency and the size of the defects?
Yes.
There's probably a limit there somewhere, right?
Yes. Well, what happens, that's a very good point, you give me the chance to comment. In civil engineering applications, let's say a building 10 stories, the fundamental mode, let's say, is 1 hertz. You get damage on the 3rd floor or something. What you're seeing is changes in low frequency things. And it turns out that we can get those modes pretty well. So now in this case, this part has frequencies on the 500 hertz. In order to actually see that crack opening, you got to get a wave that's going like that, going over that crack, right? The amplitudes are tiny. The modes are all bunched up together because the next mode is right there and so on. So the modal density complicates the situation significantly.
So your sampling density has to go up accordingly.
Our sampling density, I mean, we have an unbelievable sampling rate on this thing.
But, I mean, but how many
You mean
sensors
spatially?
do you have spatially?
Spatially, no. I mean, yes, but no.
Oh.
We don't have.
Oh,
One sensor here, another where you are. I mean,
Yeah.
And that's the competing objective.
That's the problem.
Is you want low sensors for aerospace structures as a weight and cost concerns. So how do you design in those limits?
We were trying to figure out how much we have to measure to find cracks or delaminations or debondings in a
Perfect.
pavement.
I mean, this technique, for example, what we're saying is the actuation points that are trying to locate the crack are sparse. One here, one over there. We can, however, excite at high frequencies and generate these little waves at these sparse locations. And perhaps see that under this condition, it's unobservable, and therefore there must be a node over there, which is what we're saying.